In this video, I want to talk about growth and decay models related to differential equations. So in the first video lecture, just introduction to differential equations, we talked about what it means for a function to be the solution to a differential equation. So for example, in this differential equation, what we want to find is a function y equal to f of x, such that when I take the derivative of that function, it's equal to twice x divided by the function, right? Or another way to think about that is 2 times the ratio of x to y. So in the first introduction, we only looked at what it means to be a solution. We didn't actually talk about how to find a solution. So I just want to go through one example of how we might solve this differential equation, and there'll be more on that in the video lecture on separation of variables, because that's basically the method we're going to use here. And the idea is, let's say if we just rewrite y prime as dy dx equals 2x over y. What we want to do is get all the x and dx on one side and all the y and dy on the other side. So the way to do that, if I multiply through by dx here to bring it over and multiply on this side by y, then I get y dy equals 2x dx. Now at this point, I'll integrate with respect to y here and with respect to x here. This will give me y squared over 2 plus c, and this will give me x squared plus c, our constant of integration. Now these constants might not be the same, so we often label them c1 and c2. But in fact, we can actually combine them into a single constant just to rewrite it. So if I rearrange here, I will end up with y squared over 2 minus x squared, just to get all my variables on one side. On the other side, I end up with c2 minus c1, and I can just rewrite that whole thing as just c. Finally, I'm going to multiply through by 2 just to get rid of that fraction, because nobody likes fractions, right? So if I multiply through by 2, I end up with y squared minus 2x squared equals, and I can think of this as 2c, but in the same way that I could write c2 minus c1 as c, I can write 2c as just c. Because it's just a constant, an arbitrary constant, it doesn't really matter if we find the difference between two of them or multiply them by a number or divide them by a number. It still can just be rewritten as an arbitrary constant. So this would be the general solution, and we can verify that. Let's just check that. So if I take the derivative using implicit differentiation for y squared, I get 2y times y prime minus 4x, and the derivative of any constant is 0. So let's try to solve for y prime here. I'll bring the 4x over, so I have 2y y prime equals 4x. Divide both sides by 2y. Y prime equals, and if I simplify, I get 2x over y. So indeed, this is a solution to that differential equation, because if I take this expression, which is not a function because of the y squared, if I take the derivative, then it does actually behave this way. The derivative is 2 times the ratio of x to y. Okay, so that's just a brief, introduction to how we might solve. Again, this is still a very basic differential equation, but how we would separate the variables, integrate both sides, and then solve. Okay, the next thing I want to talk about is the difference between linear and exponential, because there are a lot of situations where exponential growth or decay can be modeled, and we want to know what that means in terms of the differential equation. So for linear, the differential equation, the derivative of any linear equation is always a constant. So we can think about that in terms of like y equals mx plus b. Right? The derivative will always be the slope, right? Because b is a number, x is my variable. So let's look at a specific example. I don't know, something like maybe 2x plus 1, right? If I take the derivative of y, it's just 2. It's always going to be 2. So what this means is that the rate of change of a linear, so dy dx we can think of, remember the derivative is the rate of change. The rate of change for a linear function is constant. It's always 2, right? The rate of change is always 2. So you can think of situations, any kind of a constant growth or a constant diminishing situation would be considered linear. You might think of like an hourly wage. If I make $10 an hour, it's always $10 an hour. No matter how well, aside from overtime, but let's say it's constant. So that's the linear. The rate of change is always the same. For exponential, the rate of change is proportional to how much we have. Right. So that's what this says. It's not just a constant, but it's a constant times how much we originally had. So let's think about how we might solve this differential equation to see what kind of a function it gives us. So if we use the same idea of the separation of variables, what I want to do is get the y over here with the dy and the dx over to the other side. Right? So it's going to look like dy divided by y equals k dx. Right? So I'll integrate both sides. This is going to give me natural log of absolute value of y, and that's going to give me kx plus c. Now to solve for y, I'm going to make that the exponent of e, and I'll do the same on the other side. So that gives me y, and I get e to the kx plus c, which I could rewrite as e to the kx times e to the c. We know that if the bases are the same, then I would add the exponents, and that's what I've done here. So I've just gone in the other direction and rewriting it as a product. And e to the c, again, so I have, e is approximately 2.718. That's just a number raised to an arbitrary constant. I could rewrite that as just c, because it's still just a number. So finally, our model gives us c, and I bring that constant out in front of this, e to the kx. So here, this is where this idea of proportional growth. So some examples of that might be population growth, generally, or you think about bacteria. If you just have a few bacteria, the number of bacteria it'll grow by is proportional to how many you have. So if you have a few, the growth is smaller. If you have a lot, the growth is larger. There's a lot of situations, and we'll talk about a few more of them before the end of this, that are modeled by an exponential growth scenario. I also want to give just an example of how this leads to this. Well, just like we did previously, we can take the derivative here, right? So remember that x is my variable. E is a constant, it's the base. K is a constant. C is a constant. So if I want to find dy dx, so if we just focus on, let's not worry about the c, if we just focus on this, we know that the derivative of e to some function is just e to that function multiplied by the derivative of the function. Right? Well, the derivative of kx is just k. So I end up with k times c e to the kx. But this is y. Right? So we get dy dx equals ky. So this just shows that the exponential function certainly satisfies this idea of a rate of change that is proportional to our original amount. All right, let's look at a specific example, because this is kind of some alphabet soup here, just lots and lots of letters. Let's look at a particular example here. So what we're given is that the rate of change of y is proportional to y. So that means we're going to have an exponential growth or decay situation. And we're given two further bits of information. One is that at time 0, y equals 2, and then the second is at time 2, y equals 4. And we want to figure out what y is when t equals 3. Now, what I want to point out here is if this were linear, the way to find the rate of change, obviously, would just be to find the slope, right? So y goes up by 2 when t goes up by 2, so our slope would be 1, right? And our y-intercept would be 2. So if this were linear, we would have, 4 minus 2 over 2 minus 0, so our slope would be 1. And the y-intercept is what the value of y when t equals 0, so that's going to be 2, so we would have y equals x plus 2. This would be linear. This means that every time t goes up by 1, well, I guess this would be t, wouldn't it? Not x. Every time t goes up by 1, y goes up by 1, right? T is 1, y is 3, t is 2, y is 4, t is 3, y is 5. Every time t goes up by 1, y goes up by 1. But when they tell us that y is proportional, the rate of change of y is proportional to y, then we know it's not linear, right? So what do we do with this information? Well, we know we've already solved back here, we've already solved the general case where we saw how the rate of change of y is proportional to y. We solved that differential equation, and we ended up with this right here. All right. The only difference in this case is that our independent variable is t. So we could just start off saying, well, that we know is going to follow something that looks like this: ce to the kt. We could solve the differential equation again, but we just did that. So I'm not going to do that. We know that the solution to the differential equation looks like this. Now we need to use this information to solve for c and k. Since we have 2 points and we have 2 unknowns, we can do that. So let's start with this first one. When t equals 0, y equals 2. So I'll put in 2 for y equals c e to the k times 0, right? Well, k times 0 is 0, e to the 0 is 1, so that's just c. So that tells us that c equals 2. So let's update our model now. We know c equals 2, e to the kt. Now we use our other bit of information. We'll put in 2 for t and y equals 4. So 2e to the, and I'm going to call this 4k. Right? Okay, now we just need to solve for k. So first I can divide through by 2. So I get e to the 4k equals 2. Take the natural log of both sides. All right, because natural log of e to anything is just that thing. So 4k equals natural log of 2. And k equals natural log of 2 over 4. All right, so there's our model now. We have y equals 2 e to the natural log of 2 over 4 times t. So now we have a full model that we can use when we just put in 3 for t and solve for y. So y equals 2 e to the natural log of 2 over 4 times 3. And if you plug that into your calculator, you get approximately 3.364. Okay, so again, here what we found, we have this general solution to the differential equation. That's our general solution. And then we found over here the particular solution. This was the particular solution using the information that was given to us, 2 points that are basically on the solution curve. And then we were able to use that to determine, once we have a model, we could, we found y when t equals 3, but we could find y for any value of t once we have, once we've solved for c and k. Okay, finally, this general exponential growth model, or decay, and whether or not it's growth or decay depends on whether or not k is positive or negative. All right, so we saw here that natural log of 2 over 4, that's going to be a positive number because natural log of 1 excuse me, is 0. So natural log of anything between 0 and 1 would be negative. Natural log of 2 is going to be positive. So this is a growth model. But if we had, for example, natural log of 0.5, that would be a decay model because then k would be negative. So you can think of radioactive. So radioactive decay is one example. So you have a certain amount of a substance, and it's radioactive. It's decaying, and how fast it decays depends on how much you have. Population growth we already talked about. That's relative to how many of a certain population you already have. Also, a financial application is continuously compounded interest, right? So what you're doing is you're earning interest. And with the continuously compounded interest, so if you were to have annually compounded, that means that you earn a certain amount of interest over the year. That interest at the end of the year gets added into the principal, and the following year you're earning interest not only on the original principal but also on the interest that you earned the previous years. You're earning interest on interest. It could also be compounded monthly. It could be compounded daily. Continuously compounded means that, well, it means just that. It's continuously. It's every moment the interest is added back into the principal so that you're constantly or continuously earning interest on interest. All three of these, not to say that it's limited to these three, but these are some examples that we see in our text, follow this, this exponential model here. So I just want to go through one more example using so we'll do the radioactive decay, an example of that. So if we have 10 grams of plutonium, and plutonium has a half-life of 24,100 years, how long would it take for the plutonium to decay down to 1 gram? Well, first we need to use this information about the half-life. Right, so we have this y equals c e to the kt. This is our general model. What this tells me is that, well, so the 10 grams of plutonium, that's our original amount. So in other words, when t equals 0, sorry, not 10. When t equals 0, y equals 10. Right? So basically 10 equals c e to the 0, which is just c. So you can always think of c as kind of your original amount, because you're going to go through this process of putting in 0 in the exponent, so e to the 0 is 1. So we can update our model. It's going to be y equals 10 e to the kt. So that's one point we have. There's another point that we have, and that we get that from this information about the half-life. That tells me that when t equals 24,100, then I'll have 5 grams left. And I don't even actually really need to know what that number is. I know that, even if I didn't know it was 10 grams, then I could just say, well, it's going to be half of whatever c is. That's the half-life. It doesn't really matter what the amount is, because when I divide through, I'm going to get 1/2, right? So in this case, I'll put in 5 for y equals 10 e to the 24,100 k. K is what I want to solve for here. So again, I divide through, I get 1/2 equals e to the 24,100 k. I'm going to take natural log of both sides. All right, and again, because natural log of e to something is just the something, so I've got 24,100 k equals natural log of 0.5, and that is negative, so this, again, this is how it should be, right? We want, ultimately, if this is going to decay, k has to be negative. All right, and then we divide through by 24,100, so k equals natural log of 0.5 divided by 24,100. So now that we know what k is, and we also know what c is, we can determine how long it'll take to get down to 1 gram. So what we want to do is we want to set this equal to 1. So 1 equals 10 e to the, kind of cumbersome, but let's go ahead and put it in, natural log 0.5 divided by 24,100 t. So now we know k, and we want to solve for t. So it's similar to what we did here, except now we know k instead of t. Here we knew t and not k. All right, so, and the way that we're going to solve it's very similar, right? We'll divide through by 10 equals e to the ln 0.5 over 24,100 t. Take natural log of both sides. So I'm going to be left with natural log of 0.5 over 24,100 t equals natural log of 1/10. So if I divide natural log of 1/10 by this, I'm not going to go through all the details there, but what you end up with is 80,058 years. A little bit more than that, but I'm just going to round to the nearest year. It's going to take long enough, right? What's another 6 months? So this is an example of how we would use information, just understanding that these different scenarios follow this exponential growth or decay model. We can basically use the information given to us, plug it into our general exponential model, find the values of c and k, and then use that to answer the given question.